Howdy, y'all. Thank you for joining us here at the Vectric user group. Please, if you have any questions, don't hesitate to put them in the comment section here with everyone joining us from all over the world. I have, my favorite co-host, Sami, with me today.
And we are tuning in from the Pacific Northwest. Let us know where you're tuning in from. It's awesome. It's always great that we get to come together with folks from all over the world who are as interested in CNC as we are. So we are really stoked to nerd out about CNC and one of our favorite subjects, which is chip load and chip evacuation and chip collection. Really to kind of refine the workflows that we implement in making things every day.
Yeah, we're going to review a lot of different theories and strategies that you can implement during the design and toolpath creation stages to really encourage perfect chips and great chip evacuation. And then what we're also going to touch base on is, collecting those chips and making sure your environment stays clean and your parts are ready to pull off the machine and go into post-processing.
All right, partner, should we just jump into it?
Let's jump in.
All right.
Saddle up.
Don't you just hate when your sawdust goes everywhere? Don't you just wish there was some sort of thought through solution to maximize chip collection? So, welcome to Dust in the Wind, Not in the Air. I think that was the slogan you came up with, huh, Cory?
Yeah, no, it's how do we get these chips into the dust collector and not in the shop?
Right, awesome. So first we're going to go over some of the inspiration for the project for this particular dust shoe that Brian Fogg, one of our awesome team members, has designed and has been spending some time working on refining a DIY project that is really a more refined system and has lots of attachments and really curated options depending on your particular setup. So first,
Yeah.
let's dive into the inspiration that kind of informed some of these design decisions. So, Cory, will you first tell us a little bit about the the older, I guess, original Avid CNC's original dust shoe project?
Yeah, so this was based off of a lot of different inspiration from, more traditional dust boots. It was made from high density polyethylene or HDPE. It used a magnetic base, so it did have a breakaway feature, and was one that you could make with your CNC machine. So
Right, and that's really convenient to be able to make your dust shoe as one of your first projects, hopefully, so you can start having dust collection sooner rather than later. I used this particular one for years and it was awesome, but there's always room for improvement and customization. So another CNC legend that we definitely drew some inspiration from is Frank Howarth. And he was probably one of the first people I saw to use in kind of more of a DIY solution to do the dual hose dust boot, which is really great depending on if the machine is moving left or right, if the chips are being shot either way, that there would be more distributed collection there, right?
yeah, and Frank went way beyond the dust shoe on his dust collection system. He has a sealing attachment and a bunch of really great elements that make his machine able to collect that dust effectively.
Right, and I also have a really lovely curated playlist all about CNC dust collection. Many of the videos that are listed and included have individuals, content creators, solutions for whether they decided to purchase a dust shoe or make their own, and as well as how they integrated it into their larger dust collection system in the shop, right? CNCs are really a part of the larger ecosystem, so tying it into central dust collection is really essential. And another awesome maker that we referenced and were inspired by was Jay Bates. He made a plywood version of the dust shoe that also had the breakaway feature. I think this was really appealing because more folks have scrap plywood than scrap HDPE available. So in regards to that, this was a really approachable project, and I really liked that it was something anyone can make pretty much the first day you had your machine up and running. Okay, so let's just go ahead and jump into our strategy overview for how to approach designing a shoe, the different kinds of things you might consider when making those decisions. So Cory, do you want to take us away on some of the things you might consider with dust collection strategy?
Yeah, so the first one that I like to talk about is bit selection, and bit selection is going to help determine a couple things. It's going to help determine where the chips are going and where they're not going. And so whether it's a down cut, an up cut, or a compression bit, we should be aware of where those chips are going to be headed and be accounting for that in our toolpath strategy.
We'll also get to dive into what is a good chip and talk a little bit about chip load and chip evacuation and really how to maximize that as well.
Yeah. And then we'll talk about different custom stuff that you can do for your particular work environment. And also just the dust boot or the dust system that you're using, different tools, different materials. We could have very different dust boots and a success there.
Right. And something that Brian was sure to point out to me to consider is the materials, is not only the different attachments you might use for different materials, and we'll dive into that a little bit more, but what kind of chips and if material will create chips at all. So for example, a lot of types of foam aren't able to create chips like you can with more sheet goods like hardwood or MDF or plywood or aluminum, and really how to make adjustments for those particular things, right? So let's go ahead and talk a little bit about chip canyons and channels. So Cory, can you really fill us in on what this term, and just, I think this is a term that we kind of came up with to describe the problem, but also the solution.
Yeah. So as our tool moves through the material, if that canyon or the negative space the tool is creating is only the width of the tool, we have very little chance for those chips to come out of the canyon unless they are encouraged to come out. And so when we talk about that chip buildup, if we're not encouraging the chips from leaving the canyon, the next time that tool comes around, those chips are going to act as an insulator. So they already have a bunch of heat built into them when we created them. And then when we come back, that heat's going to continue to build and store in that canyon. And heat is going to be the fastest way for us to dull our tool, which is the fastest way to have a reduced cut quality.
Right. You know what? This analogy really reminds me of the visuals in some of our state parks. So I think of this hike called the Narrows in, I want to say it's in Zion, and it's a very, very narrow kind of canyon. So when it floods, the water just rushes down, and it's very hard to kind of get out of the way. Everything kind of gets blocked up if there's debris. But if you have that same scenario with flooding, say at someplace like Canyonlands or the Grand Canyon, because the river has carved such a taper or steps down in the canyon, it being wider at the top allows for more room for that debris, aka the chips, to kind of evacuate, right? Uh,
Yeah, so if we create a wider canyon up at the top, just as you're describing, and when we get to the bottom, those chips aren't trying to get up the walls of the narrows, but more they can climb the slope of that wider top canyon.
right, exactly. So offsetting those vectors, say for example you're doing a profile cut, and offsetting the vector, cutting that halfway through, and then cutting the final vector will allow for an additional step for that chip to kind of evacuate, which is
Yeah.
a machining strategy that Brian implemented here in the project files as well. So dust versus chips. Um, can you describe to me a little bit about why we would like to avoid dust and what we might do if we can't avoid making dust?
Yeah. So if we are making dust, ideally the scenario is we're cutting MDF, and that's because you cannot make chips with MDF. It only makes dust. And so how we make dust is we are rotating our tool too fast for our feed rate. And so we're rubbing or essentially creating such a small chip that it is considered dust. And when we are using tooling like that, essentially we're going to dull the tool a lot faster, and we're not going to evacuate the heat. This comes back to heat a little bit here. And so when we talk about inspecting our chips or our dust, if we see dust, we should slow our rotational speed of the tool down, or we should increase our feeds or our lateral movement of that tool so the tool can have more bite.
So I love hearing you talk about chip load also. This was one of our subjects for last year's Vectric user group meeting, where we kind of dived into plywood and plastics as well as aluminum and brass, and really how to refine your chip load and all of the knobs you might turn to um, make that get the ideal chip. But maybe you can
Yeah.
give us the spark notes on this subject.
Yeah, I like to use an analogy of bread. If we have a really dense bread, we can cut a perfect slice of that bread that's very thin because the density of the bread holds it together. So if we had a pound cake, we could cut a really narrow slice of bread and it would still look like a complete slice. It wouldn't be falling apart into crumbs. And if we had a lighter density like a French bread, we might have to cut that at a 1 inch thickness or 3 times as thick in order to get a perfect slice. If we tried to cut it smaller, it would just turn into crumbs. And so when we talk about chip load, what we're trying to do is slice a perfect piece of bread with different densities of materials. And so with this illustration here, you can see that red area is our chip load area. And the key is to recognize that your material plays a role in this, the tooling plays a role in it, and the vectors also play a role in it. And so we have three variables here that are all playing a role into how and what kind of chip load we can achieve. But I always go back to I'm trying to make perfect slices of bread.
Oh, I love that visual. That's awesome. So another thing you might consider is tool geometry. So this is something you might select to create, you'll consider the shape of the tool to match your material and your cut quality needs. So you might choose a down spiral in order to have a really nice surface finish on the top of your veneer. However, this does not, a down spiral bit really presses the chips downward and compresses them. So it's not as ideal for chip evacuation, which is really here, as we're talking about, that's our goal, is to maximize it. So you have to make adjustments, like for example, doing the offset toolpath to create a wider canyon. Or you can select a specific bit like an up spiral bit if you're cutting something like HDPE or aluminum in order to evacuate the chips, especially in circumstances where the bit, if compressing the chips, it would really heat the bit up too much. So a down spiral bit wouldn't necessarily be used for peck drilling or creating dense holes, because as it's creating that hole. It's jamming the chips downward, creating heat, which is reducing the life of the tool. An up spiral bit will potentially tear out the top surface of your veneer, but it does help evacuate chips. It is more ideal for something like plastics, where you want to remove the chips as much as possible, but still leaves a good surface finish on the top. It doesn't have that issue with grain direction like you do with wood. So those are some things to consider, whether it's selecting the tool for the best cut quality, but then also how to make adjustments for that tool geometry, whether it's in your CAD or your CAM, in order to get the ideal selection of or combination of choices here. And as you can see here, we'll put some of, there's an excellent video by Jonathan Katz-Moses, and he has some slow-mo footage of a down spiral bit and versus an up spiral bit versus a straight bit. So you can really see how the bit is affecting and making the material flex as it's cutting. As we were just talking about what you might consider when selecting the bit, other things you might consider are if I select multiple tools that are ideal for different types of tool paths. For example, I might have a peck drilling operation as well as a profile operation. Perhaps the ideal tool for both those tool paths are different. But if we select the same tool for both of those, that would reduce the number of tool changes that we have to do. So for example, in this project, to make it as simple and straightforward as possible, Brian programmed it with one bit, which was the 1/4 inch down spiral. In order to accommodate for that, he made some adjustments to the CAD and the CAM so that that particular tool would still work in scenarios where you might have chosen a different tool.
Yeah, we also included the appropriate ramps and additional tool paths, you know, where when we come in and make contact with the material, and then when we're down in the bottom of those canyons, there is an opportunity for those chips to get out.
So the challenges when creating your CAD and CAM is to look for the opportunities to create chip evacuation. Like Cory was just mentioning, creating a ramp and a lead-in allows more space for those chips to move out of the way of the router bit. Right, and this project might give you the opportunity to do some tests. If you're going to do a large production run of something, it might be worth it to do 5 smaller tests of that particular material with that particular setup. You know, you have specific fixed variables, which would probably be the material or the tool that you're using to cut that material for that geometry, that vector geometry, and then adjusting what attachments and then what toolpath variations you add in. Cory, can you tell us about what's a good chip? I'm partial to Pringles, but you know, Brian and I were having this debate the other day. He's more of a Dorito guy. So really, how do we determine which one is better?
You know, I gotta say, Tim's Cascade jalapeno, it's kettle cooked in peanut oil. There is no better chip.
Yeah, that's fair.
Yeah, no, when we talk about just what's a good chip, a chip is a perfect slice of bread. And what it's doing is it's taking heat away from the tool. So it's almost acting like a heat sink. In fact, it is acting as a heat sink from all that friction from creating that tearing of our material. And we want that to absorb that heat and then take it away from our tool.
Awesome. And then when you cut your chips, you were mentioning earlier, and we were talking about doing various tests. When you cut a chip and you're turning a different variable, what's the difference between an okay chip, a good chip, and a really good chip? Say, for example, we'll just use plywood as an example. Is there a particular cut finish or density or thickness that we should be looking for?
Yeah, so what makes a good chip? So you're going to be looking for tear out on the top and the bottom of your material. But more importantly, when you are looking at the chips, you should be seeing something that almost looks like crushed up popcorn. So we should be finding flakes of material. With plywood, we typically have a number or a series of veneers at cross grain glued together. So it's not going to be quite like the same chip as we would get out of a hardwood, which we should see more of a traditional chip like we would see out of other woodworking tools or a router table. But when with plywood specifically, I think it like kind of ends up looking like crushed up popcorn.
Mm.
So it's more like a Pringles versus, a Tim's Cascade, which would be more like your hardwood. It cut sliced right through the potato, nice thick chip. Where plywood or MDF, we might be more like a Pringles, where we mash up the potato and we extrude it out into a shape.
That's fair enough. So
Yep.
the way the material is fabricated will definitely play into that, and the density of it as well. So there's a few different accessories that you can design and add on and customize depending on that material that you select. So having various brush lengths will really help depending on the length of your tool. Perhaps you program two different tool paths for the same tool. Say it's a long reach tool and it cuts through halfway, and then it will stop. In the second tool path, you can switch in the shorter brush length so that reaches just the top surface of the material as it does its final passes. You can also add on a reducer from 4" to 2.5" in order to collect the chips adjacent to the tool paths. And Brian did a very clever thing here, which was to offset the tool paths, the spacing between the spindle nose and the hose on the side, so that that reducer went right above all of those canyons and was able to suck up all of the chips within the canyon itself.
The reducer allows us to remove the same CFM air, but out of a much smaller nozzle. And so we're really going to pull even more chips out of that canyon using this reducer.
Right. There's also a compressor attachment where you can direct the air to blow the chips away. So for example, when you're cutting aluminum, one of my least favorite tasks to do is to clean my brush after cutting aluminum, because it just it's full of fluid and aluminum chips stuck in it. So instead of perhaps having a brush on cutting aluminum material, you have compressor attachments that blow the chips into a directed area. There's also a lifespan to the brushes, so they are kind of a consumable object. So this design allows you to replace the brushes as necessary.
Yeah, and these are inexpensive parts that you can machine over and over again. I would encourage everyone to have, 2, 3 different brush lengths. And if you want to have 4 or 5, between your reducer and other things, nothing is stopping you here with this design. It's very accessible and cost effective.
So Clean Your Room CNC, this was a program that I used to run, and I'm sure it was something that many other CNC operators used as well. But this is just what I called it. And Cory, I'm sure you do this as well, but creating a pocket tool path in order to have your CNC run across the spoil board to clean up all of your chips and extra dust at the end of the day. It's always a really nice thing to come back to, a nice clean machine spoil board the next day. It also helps with the fact that you can't always reach to the other side of the spoil board with your shop vac, and chips can escape, so it's nice to just have a nice sweep at the end of the day.
Yeah, no, I think this is great. And you can do different versions of this. You can have one that essentially just does the perimeter, and you can have one that rasters along X or Y. And mine is saved on my desktop, and I run it all the time. And when you told me about this, it was like, wow, that's just such a simple solution. You can load the G code, you can hit start, and you walk away, and it cleans itself up.
And we'll say, remember to remove the tool before you run this. It's just nice to know that there's no tool that will accidentally scrape across any material or the spoil board, and you can just allow the brushes to do the work there.
Yeah, I also usually just kill the spindle motor after it started, just so it's not just spinning.
Right.
Well, yeah, let's look quickly here at an exploded view drawing of this particular assembly, and we'll just kind of touch base on the different parts here from top to bottom. So at the top, we have our two pipe clamps. These are going to allow for our dust collection system to be attached into the CNC machine here. And then we have the top plate. This is going to have a friction attachment to the nose of the spindle. In that top plate, we're going to have two reducer rings. These are going to give a surface for those pipe clamps to squeeze that dust collection system onto. Those are attached to the top plate with some fasteners. And then we have the bottom boot section. So the bottom boot section features the plywood boot. It also has a plywood brush retaining ring along with some magnets. And then we have a replaceable handle here. We made this handle replaceable because some people might want a different shape for their ergonomics, or maybe want to carve something into it. We also noticed that this was kind of a vulnerable area of the plywood, and so to be able to just insert a new handle would increase the lifespan of this particular boot.
Right, and now we'll let Brian go ahead and demonstrate how to assemble the dust boot, or dust crock, excuse me. Okay, so here is one of the files that we have available. Brian made a few of these, one for each of the spindle offerings that we have. So the diameter of this hole right here is the thing that you want to look for in adjusting that variable to fit your particular cutting tool, whether it's a router or a spindle. That is the diameter that you'd like to adjust on the top plate of the dust boot. There is also two hose and single hose options. So here is the single hose variation of this, and we've included the files for the 3 horsepower, 4 horsepower, and 8.7 horsepower spindles that we offer, but as I was mentioning, easily customizable to fit your particular cutting tool.
Yeah, and with V11's new feature of scaling, you could also, if you had a really small router or a really small spindle, you could maybe scale this down and have that uniform scaling. Don't you love that new feature of V11, Sammy?
Oh my gosh, it's I would have given a talk all about individual vector scaling if I had the opportunity to give another talk, and I certainly will have to do a live stream and a few videos that really dive into how you can leverage that.
It just makes modifying and evolving designs so much more fluid when you don't have to start all over, or when you can move those together.
Right. Yeah, absolutely awesome. So let's just dive into a little bit of the cam choices in this dual hose dust boot and do a quick walkthrough of this.
All right, so we have a number of different toolpaths here to make this boot, and I'd like to go through each of these toolpaths, and we're not going to touch base on every element of these toolpaths, but we do want to put special attention towards some of the cam techniques we've programmed in here to have this downcut tool have okay chip evacuation, or better than typical chip evacuation.
So this first one is a little bit of CAD and CAM. I'll just zoom in here. So this is the final profile of the interior of the dust, the brush retaining ring. And this first toolpath is the chip channel. So the vector that's selected here is the offset of the final profile. So let's open this toolpath. And we can first see that the cut depth is 2.375, so about half the thickness of the material. And we have the 1/4 inch down spiral selected. Let's check out our feeds and speeds here. Of course, these feeds and speeds are going to vary depending on your particular machine capabilities and all of those variables as well.
Yeah, but we are trying to target a chip load of somewhere between 3 and 5 thousandths thick with a material like the Baltic birch plywood we're using.
Right. Here are the counter bores. So these are the bores for the magnets to sit in.
Yeah, and if you can see here, we are using a profile toolpath rather than a pocketing toolpath.
And this really allows you to use the ramp tool in a spiral to ensure that you're having a nice ease down into the center of the inside of the vector there.
Yeah, exactly. So this is going to give us a nice smooth helical move into the material, and it's not going to give us a drilling motion, but more of a helical motion, and is going to allow for us to get a really good clean cut.
So these are the insert holes. So these are, I believe, for the threaded inserts that will hold the reducer flanges on. And we have this cutting through in the same tool that we have selected for every toolpath.
Yep.
And this is also a profile toolpath, which is implementing the same ramping strategy. So here are the through holes. This is the counter bores are kind of the lip that the edge of the magnet can sit on. And this is the space for the air and the extra glue to kind of be pushed through on the other side as you're inserting the magnet. And we'll use the same ramping strategy as we did for the other through holes as well, with the smaller interior diameter.
Yeah, and with this downcut tool specifically, if we were to try to implement a pocketing style toolpath in this area, we would essentially be coming straight down into the material in a plunge in the center, and then we'd work our way out at that depth of cut. And with that downcut tool, that's really going to increase the heat the heat that's built up in the tip of that tool.
Right. Next we have the relief, and this is for the brush retaining ring and the brush to sit into. So that's really pressure fit into that space.
Yeah, and this might be another area that you make some small modifications to, depending on the type of brush that you have. And so in the event that your brush is a little bit thinner or thicker than the brush we have listed on the bill of materials, you might adjust this retaining ring.
Here is the relief number 2. So this is to give an additional canyon here and lip for this part to nest together into the top plate or the brush plate. So the next toolpath we have here is the, there we go, bring it to a good view for you. This is a relief. This is a relief for those reduction flanges to sit into. So making sure that the diameter of those match the particular material or part that you have sourced. This will work with the one that we have on our bill of materials, but if you have a couple extra lying around, might as well use those and make that minor adjustment. Here's a small pocket detail for a little addition on the handle here. Then here's the spindle nose bore, which is the final pass here. What I will note is in the CAD is we have a little dip here and a dip here. This line is indicated as a cut line that you will make with a small handsaw in order to put your screw through here to pressure fit and just have a little extra fastener to hold this top plate to your spindle.
Yeah, I think this was a great design element by Brian. He put 2 small detents in these tool paths, and so when you go to make that cut, all you have to do is line the saw up with those 2 detents and it's in the perfect position.
Right, and it's got some good tolerance variation there. You know, we know it's you're using handsaw, but the tolerance is open enough that as long as it's between these 2 marks, it'll be very easy to do. And you can definitely see the J. Bates design influence there.
Big time.
And then lastly, we have the interior profiles as well as the outer profiles. So we have the channels that cut a lot of the extra canyons for chip evacuation, and then there is the final profiles. So let's go ahead and do a quick preview of our toolpaths.
And I love that Vectric allows for you to preview these independently or all together on a lot of different speeds. And sometimes when designing in a 2D drawing environment like this toolpath creation area is critical in regards to making sure the right sequence is happening and the materials being removed in the way you anticipate.
So that is the new dust boot design that we will be creating further content about, the step-by-step how to set up and run it on Mach 4, and that will be coming out on our channel soon. So if you all have any questions, I guess we'll go ahead and jump into a Q&A. Any other last thoughts you'd like to add here?
Well, it's been a long road, but I'm ready for the questions. Let's do it.
All right. Hello, everyone. Thank you so much for tuning in and for all the awesome questions in the chat here that we've kind of been having such a great conversation to hear about everyone else's strategies and how they approach specific types of tool paths and router bit selections for specific types of tool paths, and how you approach all of those things. So if you have any questions, I'm happy to answer those now. And maybe I'll just revisit a few that we had earlier that we're kind of chatting about. There was a few references I just wanted to reiterate so that you might be able to follow up on them. There was the Jonathan Katz-Moses slow-mo video. I really would encourage you to go back and watch that. He rented a really incredible camera to film those router bits in action, to really see exactly how the material works or is moving in the movement caused by those bits and the specific geometry. So that was an excellent video. And let's see, get some questions here. I'd also recommend you follow up on Alexander Chappelle's video. He's a new person we've been working with, and he has amazing videos. He's been primarily making he has a lot of digital fabrication experience, but has primarily focused on 3D printing and that sort of thing. So it's awesome to see CNC really being, or machining specifically, being integrated into his workflow. I'm just going to read through these questions really quick. No hat, I know. It's over there. I forgot it. It's hard to wear my hat with my headphones as well. So yeah, so I also wanted to what indicates that you're cutting too fast in the material? I see. I guess it really depends on what type of material you're using. There's just so many variables in regards to how fast. I guess I would look for things like tool chatter and that sort of thing, and your cut quality, and you probably won't have burning at that point, but your chips might not be. You're kind of going for too high of a chip load, which is kind of putting too much force on your bit. Do you make much use of the toolpath templates to capture these multi-pass toolpaths and then reuse them? Yeah, so that's, I love the template. I think that was integrated in 10.5, I believe. It just is, it's such an awesome tool. The other one I am update recently I'm super excited about is the individual vector scaling. So for example, being able to select every hole that you have on a pegboard design and being able to scale those individually so they stay scaled on center rather than scaling them as a group, that I could absolutely go nerd out about for sure, which would also be relevant, you know, if you have a different hardware available, a different size threaded insert on this project, for example, and you wanted to change the screw size using that tool, that feature would be really beneficial here as well as the multi-sheet update as well. Multi-sheet, I'm super stoked about it. It's a good starting point. The feeds and speeds in the chip calculator, a good starting point. So I guess the speeds and the chip calculator. So, well, it depends what tool library you're using, kind of what the default settings are for that particular tool. The chip calculator built in is going to reference those settings. So I'm wondering if you're just talking about the default tool settings there. Maybe you can help me clarify on that specific question. I think I did mention just now Alexander Chappelle. The way he to go back to the different brush lengths. If you look at the way you mount your dust boot, this particular one is mounted to the spindle and the spindle nose, but the way Alex does it is it's attached to the side of the Z-axis and it has an independent movement up and down. Now Izzy Swan takes this even farther by adding a second Z-axis and then adding the dust boot to that in order to move it with the controller. But I think that's not, depending if you're doing specific sheet goods, it's not super necessary. Alex also had this very clever flexible vacuum component, which would allow you to lift it up and down, and it didn't have to be the exact same diameter as the spindle nose itself. Will we see ATC from Avid anytime soon? It's something that we definitely are putting resources to and are very much looking forward to. I can't wait to see it just as much as you. So that is something that we are working on. I'm sorry I can't give you any specific timelines, but because our machines are so modular, they have a flexible architecture and design, being able to add on and expand your machine. We always work really hard to make sure our machines are kind of backwards compatible, or at least have an upgrade path. So we want to make sure that anything we come out with is really works for all of our customers, new and current, and lots of our legacy customers as well. Okay, I'm not getting burning, but wondering. Okay, so you're just trying to understand what to look for when you're pushing your cutting rates too far. I guess the things I would see would be the most obvious when I'm pushing the machine kind of past its limits, or the tool past its limits in that particular scenario, is if I'm getting a bad cut quality. So if the tool is chattering, especially if you have a smaller diameter tool, anything 1/4 inch or lower or smaller, I usually see the tool kind of variable and characteristics fail first. The offsets, you'll have a kind of a lower cut quality there. I think that's kind of when I would see that first. That's probably what I would look for, because I find, oh yeah, there Cory's giving us a little ATC update. Right. Well, thanks everyone so much for all of your questions and for being here. We will be back in a little bit, just in about 10 minutes for the next talk. Thank you, Vectric, so much for hosting this event. We really appreciate you and getting to be here. So I'll see y'all soon. Happy making.